Okay. Assalamualaikum. I'm trying my best lah to handle this session in Dwi language, Bahasa Melayu and Kelantan English. Okay, let us open our program today by reciting Umul Kitab Al-Fatihah. Auzubillahi minasyaitonir rajim. Bismillah. Okay. A warm welcome to our distinguished guests, ladies and gentlemen. Assalamualaikum warahmatullahi taala wabarakatuh, and good afternoon. I'm Zamili bin Muhammad, and it's my pleasure to be the moderator for this session. Today we have a very special speaker from the field of photonics, and he is Associate Professor Dr. Muhammad Hafiz Abu Bakar. Dr. Hafiz obtained his Bachelor of Electronics majoring in computer at Multimedia University and his PhD at University Putra Malaysia in photonic and fiber optic systems engineering. In 2016, he was the recipient of the UPM Vice Chancellor Fellowship for the Young Researcher in Science and Technology. Without further ado, welcome Dr. Hafiz to deliver this lecture about fiber optic loss characterization.
Thank you, Mr. Zamili. Well thought of opening speech. Okay, I assume there's a script in front of you. Okay, so today's talk will be quite a concise, somewhat of an overview of the factors as well as methods that are involved in loss characterizations of fiber optic. The intention is actually to provide more information, firstly to the assistant engineer, okay, in order for us to produce more people, more skilled personnel in handling our labs, okay. So, but of course, it will serve as a good knowledge as well to the rest of the participants. Okay, all right. So I will start my talk. Okay. Okay. So for those that just came in, okay, my name is Muhammad Hafiz Abu Bakar. So I'm the head of the photonics lab, and I've been in the field. Okay, I've been in the lab since 2012. Okay, if I'm not mistaken. So I'm going to, next year will be my 10th year in UPM. Okay, so I've been working in the field of lasers and amplifiers. Okay, and recently ventured more towards optical fiber sensing. Okay, all right. So we're going to start with the outline of the presentation. Okay. First, we're going to talk some basics on the operating principle. So how does fiber optic work? So it's a very concise look on the theories on confining light, okay, in fiber optics. Then we will look into the loss and attenuation in optical fibers. So what are the factors? Okay. So we're going to have some overview on that. And then we're going to look into some of the more common methods to characterize loss in optical fiber. And lastly, a summary of the talk. Right, so for the operating principle, it will be more focused on the basic concept, which is the total internal reflection. And of course, we can't talk about total internal reflection without talking about refraction, pembiasan. So in general, so refraction is the bending of light as it travels from one medium to another medium with different refractive index. So I think we've learned this in our secondary school, okay, at least. Right, so we see how light as it travels from a medium with, I think we usually see this in a glass of water, how a pencil seems to be bended, okay, when it is immersed, okay, half of it is immersed in water. So it's a concept that is common to us. Okay, so the main theory, okay, behind why light is refracted is due to the difference in light velocity as it travels through the two media. So the main condition is that the media has to, both of them are of two different refractive indexes, okay, and it has to reach the boundary between the two media at an angle. So this image is an example, okay. So in the image on the left, okay, this is a case where the light travels from a medium with a refractive index that is lower than the refractive index of the second medium. So you can see here that the light ray represented by this red arrow, it incident at the boundary, okay, at an angle, so it's not coming from a straight line. So what happened is that in this condition, okay, so the light is bended nearer towards the normal line, okay, and the opposite happens when light travels from a media or medium with a higher refractive index to a medium of lower refractive index. So here the light is bended away from the normal line. So those are the concept behind refraction. So how does the velocity or the speed of light affects causes this bending? So we can an analogy of this concept, okay, can be represented by this image here. So we can think of it as okay. So these are five guys. Okay, they are good friends. Okay, so they are coming from the beach into the water. Okay, so it is logical, okay, to say that we can move faster on land compared to in the water, unless you are Aquaman or you are a fish. Okay, so these five friends, okay, so they are very close to each other and they are holding hands while they are traveling towards the water. So now we are assuming that all of them are of the same height, okay, and their steps are the same. So that means the speed of them traveling into the water is the same. Okay, so since they come at a straight line, okay, so they reach the boundary here, okay, the teeth, okay, gigi air ini, okay, not at an angle, so the same as a normal line. So what happened is that the speed is slow, okay, the speed changes, okay, they all become slow at the same time, okay, and the speed is the same, okay. As a result, no bending, okay, occurs. Their direction, okay, as they move towards the water is always the same, okay, in a straight line. So what would happen if they come at an angle? Okay, so again on land, okay, so their speed is the same for all five of them. So now they reach the water at an angle, and due to this angle, okay, the person here on the left will be the ones reaching the water first before the person on the right. Okay? So as this occurs, so the person on the left will become slower compared to the person on the right. So now the speed is not the same. As a result, the person on the left will act as a pivot, okay, and shifted the direction of everyone, because he is slower, but the rest of the guys are still faster. Okay, so due to this effect, okay, so you can see that their direction, okay, as they hit into the water and as they travel, okay, after all of them reaching the water, will not be the same as their original direction. Okay, so this is a concept, okay, that can be considered similar to when light travels from a medium with lower refractive index into a medium with higher refractive index, where the light is bended nearer to the normal line. Okay, so a straight line that is perpendicular, okay, to the boundary. So as they travel, okay, out from the water, okay, again, if they come at a straight line, so they all will, their speed, okay, will be increasing similarly for everyone. Okay, so there will be no change in direction. Okay, so the effect is different if they exit the water at an angle. Okay, so what happened here is the person to the left will become faster first, okay, compared to the rest of the friends. Okay. As a result, their direction will be shifted, okay, to the right, and their direction will become bended away from the normal line. So this is similar to what we can observe in light propagation. So when light travels from a medium of a higher refractive index to a medium of lower refractive index at an angle. Okay, so that is the analogy that we can use to imagine how the concept of refraction happen. Okay. So this is the concept that is leveraged uh, by in optical fiber. So what we have is a core of a higher refractive index that is surrounded by the cladding layer. Okay, so the cladding layer is of a lower refractive index compared to the core. So when light travels in this optical fiber, if the light incident at an not at an angle, okay, similarly to the normal line, so you can see that there is no refraction occurring, okay, and the light will actually leak outside. So this behavior, okay, so you can start to see some refraction occurring, okay, as the light reaches the boundary at an angle. However, there is an angle that we define as the critical angle, which is referred to as an angle where the refracted light has a 90-degree angle to the normal line. Okay, so if the angle of the incident light is less than the critical angle, so we have not yet reached the total internal reflection. So this occurs only at this point where the resulting refracted light will be refracted parallel, okay, to the boundary, as described by this particular example. So this is the critical angle that is the point of initiation of your total internal reflection. So any angle that goes beyond this critical angle will allow light to be refracted or reflected back into the optical fiber, hence allowing the light to be confined in the fiber, and the light can continue to propagate forward. Okay, so that's the basic concept that is that utilizes the theory of refraction and is used to govern light propagation in optical fiber. So this is a common example of total internal reflection. So you can see here that you have a strong ray of light that is seen to be propagating, okay, from one end to the other end. Here you can also notice that there is some shades of red that is coming out, okay, on the outside of this spec, okay. So these are all the lights that was not able to conform the critical angle rule as a result. So these are the lights that leak outside, okay. So that's the whole idea of total internal reflection. Okay, so now we will look into the factors contributing to fiber loss. So these are the main three main factors, okay, that can cause loss in a fiber. Okay, so the first is absorption. So absorption is the transference of energy, okay, that is contained in light propagating within the fiber to what we commonly refer to as water. So what happened is that during the fabrication of a fiber, okay, so some amount of water, okay, usually in our atmosphere will be trapped, okay, within the fiber, okay. So this leaves behind some hydroxyl ions, okay, that will continue to be present, okay, in the optical fiber. So these hydroxyl ions will actually absorb energy, okay. So we can look at it as someone who likes to eat a certain particular type of food, okay. And in this, in the case of this hydroxyl ion, so the focus is actually on energy or light at wavelength of 1.3 micrometer. Okay. So as a result, light that is propagating in optical fiber will actually suffer a significant amount of loss, okay, around 1.3 micrometer due to the presence of hydroxyl ions or water loss. Okay. Right. And we also have what we call scattering, right? So scattering is a deviation of light, okay, due to non-uniformities. Okay, so that means the internal. Okay, so as light travels through the fiber, so it will encounter a lot of non-uniformities as well as impurities. Okay, so this scattering can occur in all directions. Okay, it can actually go forward, it can actually go out, and it can actually go backwards. Okay, so for lights that are scattered forward, so there is it's not an issue because it's still it will still be propagating in the same direction as the original intention. So the problem is light that is actually scattered to directions other than forward. Okay, so those are the lights that will be categorized as a loss. Okay, so the most influential amount of scattering that contributes to loss in optical fiber is the Rayleigh scattering. So in the production of an optical fiber, okay, so we use heat. So there's a lot. Basically, we melt a glass, okay, and then we pull the melted glass in order to create our narrowed optical fiber. So this process creates some refractive index variation in our optical fiber. So as light travels through the fiber, okay, so it will encounter this refractive index variation. Okay, and since propagation of light is affected by refractive index, so some of these lights will actually be scattered in multiple directions. So in really, there's a lot of scattering that actually occurs in the opposite direction. That means it comes back to the direction in the opposite direction of the input light, to the direction of the user. Okay. And lastly, this is a more physical type of loss, which is loss due to bending. So there are two types of bending, macro bending and micro bending. So in the case of macro bending, this is actually a physical effects that is subjected externally. Okay, so that means when you are laying an optical fiber, okay, installing optical fiber, so is there a lot of bending, okay, at an angle that is too high, maybe. Okay, so this is why for those that have been working with optical fiber, you can see that that when we try to, arrange our setup neatly, so we have to create a loop, a big loop, for the excess fiber. Okay, so in order for us to minimize the effect of macro bending, because if you bend the fiber too much, okay, so it will be harder to achieve total internal reflection. Okay, that means the critical angle will also be different. Okay, so this might cause more light to actually be refracted out rather than achieve total internal reflection and propagate as we intend it to be. Okay, so that's the idea of macro bending. And then we also have what we call as micro bending. So in the case of micro bending, these are physical bends, okay, that appears within the optical fiber itself. Okay, so for instance, during the fabrication process, so there might be some non-uniformity. Okay, maybe there's some groove, some defect in the core, for instance. So whenever light is incident to this defect area, so the critical angle will be different compared to the normal part of the fiber. As a result, light that actually hit these particular defects will be refracted outwards. Okay, so you can see the examples here. Okay, so those that one is a bit tougher for end users like us to control, because we are not fabricating the fiber ourselves. Okay, but in the case of macro bending, so this is a good practice to ensure that the loop that you create when you want to tidy up your setup is not too small. Okay, so that's the idea behind bending loss in optical fiber. So the two main types of loss there that we've mentioned earlier, which is the absorption as well as the Rayleigh scattering. Okay, so they contribute to this loss spectrum. Okay, so this is a common loss spectrum that we can actually see from the internet. Okay, so you can see that the orange colored lines here. So this is a very major type of loss. Okay, so this is caused by Rayleigh scattering. And you can see there are several peaks, okay, that is attributed to hydroxyl ions absorption with the highest loss seen around 1.3 to 1.4 micrometer. So this is the water peak. We call it as a water peak. All right. So apart from that, we also have losses contributed by connections. Okay. So on the left here, we can see what would happen when we have a less than ideal splicing conditions. Okay. So if the fuse time is too long or too hot, auto feed is too strong, okay, the auto feed stage is too slow, okay. So these are all the errors that could occur during splicing of your fiber. In the case of a good splice, you can see that there is a proper matching between the core as well as the cladding. And in this case, we can assume that the loss that can be ignored, okay, is anything below 0.03 dB. Okay? So anything above that, we consider as a loss that we need to take into account. And we also have these types of losses. Okay, so you can see you have a lateral offset where there is a mismatch in the connectors. Okay, angles that are not aligned properly, creating an angle such as this. Okay, different numerical aperture. So that means the light that is coming out from one end of the fiber, okay, doesn't match the light collection capability of the other fiber. And then we also have core diameter mismatch, okay, off center or non-circular type of core, right? We also have cladding diameter mismatch. So these are all the types of connections that could create or contribute to losses in our optical fiber. So this is something that we can see. Okay, so the downward trajectory here. So under if we assume that there is no loss from these connections, we can see a relatively smooth decline from the transmitter to the receiver. So the smooth decline can be attributed to the normal loss, okay, such as through Rayleigh scattering or through absorption. Okay. However, in this particular example, you can see that there are some losses. Okay, so sudden decline here that is attributed to the use of connectors in this span. So as a result, the total loss that will be subjected to this system will be a combination of the loss inherent to the fiber, okay, as well as the summation of the loss contributed by the connections. Okay. So we're going to look into the characterization methods. So the easiest way to look at it is to perform simple calculation. So this is a normal fiber measurement setup. You have a light source at one end, and you have a power meter at the other end, and you can put the fiber under test in between, connected to both of them, right? So in the case of simple calculation, all you have to do is you have to know the input power. Okay, so how much power that is given, okay, by the light source, right? And then you have to know the fiber length, right? So this can be done through the manufacturer's spec sheet, okay? And then all you have to do is measure the receive power, okay? So once you turn on the light source and the light passes through the fiber, so the power meter will measure whatever power that is left after the light encounters whatever losses along the fiber. Okay? So then all you have to do is calculate power input minus power output. Okay, so that will give you the total loss of the fiber, and you can actually find the attenuation or the loss coefficient of the fiber simply by dividing loss to the length of the fiber. Okay, so this is an example. If we assume that the light source has an output of 5 dBn, and then we measure uh, the resulting power at the power meter to be 4 dBn. So that means the fiber has a total loss of 1 dB. And then the attenuation can be simply calculated by 1 dB divided by the length of the fiber. In our example, it's 5 kilometer. So now we know that the attenuation of the fiber is 0.2 dB per kilometer. So the downside of this method is that we have no certainty, okay, in terms of the input power, for instance. Okay, so we might be setting the light, okay, to produce an output of 5 dBn, but is it really giving us 5 dBn, for instance? Okay, so and then we also have no idea whether there's any defects, okay, within the fiber. Okay, so as a result, this is more of an estimation. So if you want to do a quick calculation, okay, this method is somewhat acceptable. Okay, but if you're looking to perform your, okay, in the case of a MSKK student, your dissertation project, or if you want to do your PhD work, master by research work, so uh, performing this method as the main characterization approach would not be advisable. Okay, right. So what I always advise my students to do, okay, I consider this to be a more accurate approach to characterizing loss, okay, is by the comparison method. So here what we usually do is we take a reference power. So that is simply that is done simply by connecting, okay, so directly connecting your light source to a power meter. So you can use a very short fiber, okay, as the connector. Okay, so since the loss of a normal fiber is calculated in kilometers, so if you use a very short fiber, so we can assume that the loss within this short piece of fiber to be negligible, right? So then after we get the reference power, so this will give us the exact value of the power that can be produced, okay, that can be transmitted from our light source. So then what we do next is that we disconnect the original fiber piece here, okay, and we can add whatever device under test in between. Okay, so we do not replace this section of fiber completely, okay, because we whatever the reference power that we have initially is a combination of whatever power of light coming from the source plus whatever loss that is within our fiber. Okay, so as a result, in order for us to get a fair comparison, we have to allow this fiber to remain, okay, in our setup. So what we do is that we disconnect in the middle, and we can add whatever device under test. So it can be an optical fiber, it can be connection, okay, specific connection. We want to try a different types of connector or splicing, for instance, or it could also be an optical component. Yeah, so you want to know how much loss will you incur when you use a certain type of component. Okay, so you can use this method. So then all you have to do is to minus the power measured with the device under test from the initial reference power. Okay, so this will give you the total loss contributed by whatever device under test. Okay. So one of the more, how should I say, an automatic approach, okay, to measuring losses in optical fiber is to use the optical time domain reflectometer, or in short, our OTDR. So it is basically an optical device that measures reflection, okay, and this measurement is performed in time domain. So I think those that graduated from our bachelor program would have some experience working with OTDR. Okay. All right. So the idea of OTDR is that it relies on the Rayleigh backscattering. Okay. So as light travels through the fiber at a certain speed, okay, so a portion of the light will be backscattered through the Rayleigh effect. Okay? And this backscattering will occur throughout the fiber. Okay, so that is the idea behind Rayleigh backscattering. And the measurements of the loss, the distance that the light travels can be performed, okay, by looking at the time. So you can look at the example below here. Okay, so you can see, okay, in this example, so we have a pulse that is transmitted at t equal to 0 second. Okay, so at the start we transmit a pulse. Okay, and reflection was detected at t equal to 0.001 second. Okay, so this reflection is caused by Rayleigh backscattering. Okay, so the OTDR will send out the pulse, and then it will detect whatever light that is reflected back, okay, to the device. Okay, and it will look at this reflection in time domain. So when it detects a reflection at t equal to 0.001 second, so assuming the speed of light in fiber to be 2 to the power of 10 minus 8, okay, so because speed is speed of light divided by the refractive index, so let's just assume this number. Okay, and if the reflection is measured at t equal to 0.001 second, then the light can be calculated to have traveled 200 kilometer. Okay, so since the light basically has to travel in two directions, that means it has to go from left to right first, and then reflected back from right to left. Okay, so we can calculate that this particular reflection, okay, has traveled at least 100 kilometer in fiber length. Okay, so you divide by 2. So that's how OTDR measures the length of a fiber using the concept of Rayleigh backscattering. So this is the type of reflection that we can see. Okay, so as the light travels through the fiber, okay, so the light will actually become lower and lower due to your normal scattering and absorption and whatever in the fiber. So as a result, the reflection will also decrease similarly. Okay. However, whenever the light encounters any connections, okay, or any defects or any loss within the fiber, this will also be reflected in the reflectance spectrum. Okay, so you can see that in the case of a connector, so there might be an increase in reflectance. Okay, so this can be this will be collected by your OTDR, okay, as one event. right? And a splicing loss, for instance, will induce loss. When there's a loss in the transmission light, there will also be a loss in the reflectance as well. Okay, so loss of probe power due to splice, so reflectance will also become lower. And based on this reflectance spectrum, okay, so the fiber loss can be determined through the difference in reflected power between 2 points. Okay, so the OTDR basically calculate the reflection power at 1 kilometer, and then it measures a second location, the reflection power at a second location. So based on the distance between them and the difference in power, it will be able to determine the total amount of loss as well as the attenuation of the fiber. Okay, so that's the idea behind OTDR measurements. So for the ones that we have in the lab, okay, so this is our X4 FTB -1. Okay, so this is the model of OTDR in the lab. So it has 4 main options that we can fiddle with. So we have wavelength, okay, which basically controls the wavelength of the probe signal. We have range, which basically determines the length of the fiber tested. We have the pulse. So this refers to the pulse width or the pulse duration of the pulse signal, of the probe signal. And lastly, we have the duration, which is how long will the testing be performed. So we will look into the idea or the consideration that we have for each specific feature, for each specific option. So first we will look in terms of wavelength. So this option determines the wavelength of light transmitted by the OTDR. So in the case of our X4 OTDR, we have 2 options, which is at 1300 nanometer or 1500 nanometer. Okay, so we can choose either or both. In this particular case, the test will be performed in sequence. Okay, first for 1300 and then 1500. So in one testing. Okay, so the idea behind the choice, okay, of whether to perform at our test at 1300 nanometer or 1500 nanometer will be based on whether first, if we want to know a loss at a specific wavelength. So both of these wavelength refer to the our common communication band. So you have your O band, the original band, which is around 1300, and we have the current communication band, which is in C band. So if you want to look, if you want to know the suitability of this fiber for either of these 2 communication band, so you can choose the wavelengths that is specific to your intended operating range. Okay, so that's the first idea. Okay, and there might be a case where you are testing fiber that seems to be very long. Okay, so in this particular case, you might be more concerned with getting the right results. Okay, getting to know the exact length of the fiber rather than loss at a specific wavelength. So in this particular case, you might tailor your option here, okay, to choose wavelength that has a lower loss. Okay, so in this, in our case, it's the C band. Okay, so even though say your idea is to actually operate it around O band, but because the fiber is too long and you're worried that the loss might be too much for the OTDR, so you say, okay, I don't mind testing at a different wavelength as long as I know what is the total length of this fiber. Okay, so then you choose to transmit your probe signal at 1500 nanometer. So those are the considerations in terms of wavelength. And then you have your measurement range. So in terms of your measurement range, so this basically the idea is to denote what is the estimated length. Okay, so if you buy from the manufacturer and you know what is the manufacturer's specified length, so then maybe your intention was is to determine the loss of the fiber, for instance. So then you can choose the length that is appropriate to that matches the manufacturer's specification. But in the case that you got a fiber, for instance, we did in the past, our lab, we did get some fibers that are actually donated by some companies. So we don't have the exact length. We don't know the exact length of fiber. So in this particular case, we can try and estimate or guess, okay, the length of that fiber, and we can change the range in order to see whether the choice is appropriate for that length of fiber or not. Okay, so what happens when you choose the range? First, it determines the measurement span. So basically, it determines the display here, right? So in our example here, in this image here, so this fiber actually goes maybe to a certain kilometer. So if you choose a range that is shorter than this, so you will only be able to measure up to, for instance, this part. Okay, so you won't be able to see what's happening beyond the measurement range that you have chosen. Okay, another reason, okay, that we want to choose a proper measurement range, okay, is that this choice determines the interval between the pulse. Okay, so in order to perform OTDR test, we cannot send multiple pulses at the same time. Okay, it will be difficult for the OTDR, for the device to detect the reflection, to distinguish the reflection from different pulses. So that means it has to send out one pulse and wait for that pulse to settle its measurement before it sends out another pulse. Okay, so in order for it to do this, it needs to know or have some estimation on the length of the fiber. So if you choose a length that is too short, okay, so the device might think, okay, so based on my calculation, after maybe a few seconds after the first pulse, I can send out the second pulse because it assumes that the fiber is very short. Okay, but if the fiber is actually very long, longer than the estimated range, so what happens now? You have more than one pulse present within your fiber, and as a result, you'll be getting a lot of noise. So it'll be tougher for the device to accurately measure the reflection. Okay, so it's important that we choose a range that fits our intended length of fiber. Okay, and then we look at the choice of pulse width or pulse duration. Okay, so we might be in one case we might want to have a longer pulse width or longer pulse duration, because the longer the pulse is, okay, the more power that we have. Okay, so it's self-explanatory lah. If we look at this picture, this example here, so you can see that the ones with longer pulse will have more power. So by having more power, you can actually investigate fiber at longer distance, okay, better, and you can have stronger reflectance. Okay, so it's easier for your OTDR to identify, okay, any reflection within your tested fiber. Okay, so that's the case going in favor of having longer pulse width. One thing that we have to consider, however, is that if your pulse width is long, okay, and if there is an event that occurs at a spacing shorter than your pulse width, instead of seeing two separate events, okay, you will be actually measuring an envelope of the two events. Okay, so in this particular example here, you can see that there is two connection, okay, within this fiber, okay, and if your pulse width is shorter than the spacing between these two events, so what happens is that as it travels through the first connection, it will be registered as one reflectance, and then the pulse will move and basically clear this particular region before it encounters the second connection. So, and then this will be registered, this will be portrayed as a second reflectance. So based on this, the OTDR can actually show that at this particular location, you actually have two connections or two events occurring within a short distance. Okay. But if you choose a long pulse width, okay, and it might encounter the first event, okay, first, all right, and then as it passes through the first event, okay, before the pulse width completely clear this first event, it has already encountered the second connection. Okay, so what happened is that instead of seeing two separate reflection, so both of these reflection will actually be combined, okay, as a single envelope here, and the OTDR will actually look at this as one single event. Okay, so you won't know that there is actually two separate reflection occurring at that particular location. So that's the pros and cons, the considerations that we have to keep in mind when we want to determine the pulse width of your OTDR. Okay. And lastly is the duration of the test. Okay. So as long as the test is still performed, okay, after the completion of, let's say, the first pulse, okay, the OTDR will send out the second pulse, the third pulse, and so forth, as long as it has not reached the end of the testing duration. Okay, so when you have a longer testing duration, so you'll allow more pulses to be sent. That means you can collect more information, and this information will be averaged. Okay, so if you use a short pulse duration, so that means the number of tests that you perform will be lesser, will be fewer. Okay, and hence it will not be able to properly smooth out any dynamic readings. So this will usually be reflected in this noisy spectrum. But if you choose a spectrum that time duration, okay, testing duration that is too long, okay, so there's a chance that you might smooth out too much information, okay, so which is also not good, okay, and you will also have to take a long time, okay, it will take longer for the testing to finish, okay, so that will be an issue as well. So there is a sweet spot, okay, that we have to test ourselves, okay, in order for us to get a spectrum that is that mitigates all the noises, but does not remove any events. So that's the idea behind the choice of testing duration. Right. So this is we are almost at the end. So last thing that we have to consider in the use of OTDR is that in the spectrum we can actually see a very large peak at the beginning of the reflection spectrum. So this is actually caused, okay, since our pulse from the OTDR, okay, so at the start of your connection is still high, so you will have a very high reflection at the boundary between the output of the OTDR to the input of the fiber. So this is a zoom in view of what's happening at this initial pulse here. Okay. So due to this presence of this high peak, okay, so it will actually create a dead zone. Okay. So this dead zone. Okay. So this dead zone will okay. So this dead zone will be shown in the okay. All right. Okay. So this dead zone will be shown in the spectrum. Okay. To be a pulse that spans up to in the case of our X4 could be up to a few hundred meters. Okay, so within this dead zone, okay, so whatever event, okay, any reflection or any loss that occurs to the fiber will not be shown in this section. Okay, so it's basically a blind spot for the OTDR. Okay, so what happened is that in order for us to counter this issue, we include what we call a launch fiber or a launch cable, okay, to address this issue of dead zone. So this launch cable, okay, it has to be a fiber that is known to us. Okay, so let's say from in this example, from this particular connector until the end, so this is the fiber that we want to test. We don't know the exact condition of that fiber. Okay, so we add, okay, a section of fiber that corresponds to the length of your dead zone. Okay, so this fiber should be a good fiber known to us. We know that it's in good condition. It has no how should we say unnecessary or extra loss compared to a normal fiber. Okay, so then we use this here. As a result, the blank spot will be confined, okay, within this launch fiber. Okay, so this launch fiber will actually correspond to this, the length of your dead zone. So whatever event that starts to occur after this dead zone will be able to be reflected in the optical, in the reflectance spectrum. So that's the idea behind having a launch fiber. All right, so we are at the end of the talk. So in summary, so I've given an overview of light propagation in fiber optic, the concept of refraction and total internal reflection. So we've talked about factors influencing loss in fiber optic. So the water absorption, Rayleigh scattering, the different types of bending as well as losses contributed by connectors or connections. And we have also looked into methods to determine loss. So we've looked into simple calculation. We've looked into the comparison methods, as well as the use of optical time domain reflectometer. Okay, so that's all from me. I welcome any question.
Okay, thank you very much to Dr. Hafiz for giving such an informative and interesting lecture. To participants, if you have questions, you can write in the chat box. Also, please be reminded to register your attendance by clicking on the Google Form link in chat box. Okay, tak ada soalan. Okay, Dr. Hafiz, I have one question. Are you ready to answer?
Yes, yes. Seriously.
Okay, you have given us a clear picture on how refraction occurs, and that one of the main rules is that it happens when light travels between two media with different refractive indices. Could you elaborate more on what refractive index is and how it calculate? Thank you.
All right. So the basic idea uh, of a refractive index is that it measures the optical density. So optical density, in general, you can look at it as how well, okay, a light travels through a certain transparent medium. Okay, so in this particular case, as light travels through a medium with higher optical density, we can look at it as it has to interact with more electrons, okay, more ions within this particular medium, okay. So due to this multiple interaction, so the more interaction that it has to go through, the higher the optical density. Hence, the light will be slower. So this is referred to as a condition of high refractive index. So that is how they define refractive indexes.
Oh, I see. All right. Any question? Okay, I ask. Question number 2. It seems like optical losses are unavoidable. Are they costly when it comes to the deployment of fiber optic networks?
Right. The when we talk about costs, we always have to look at it, in my opinion, in some sort of a comparative way. Okay, so for instance, we might say that using copper wire, for instance, would be a lot cheaper. It's something that is more available, more ready in our current in the current world. However, if you look in terms of loss, for instance, the loss of copper wire, okay, is about 20 dB per kilometer, right? And the loss is actually dependent on the frequency of the transmission. So that means the higher your frequency is, the higher the loss will be, which is why we have speed limitations in copper punya transmission. Okay, so we can actually put this into how should I say comparison with optical fiber. So you might the 0.2 dB per loss is 100 times better than copper wire. But of course, you have the cost of, say, the production is not, the cost of production is definitely higher than copper. Okay, so you also have issues with, in terms of, say, the fragility. Of course, is a lot more fragile to when compared to copper wire, you know. So I think any talk about cost versus loss, you have to balance it out. So you get lower, 100 times lower loss, but at a higher cost with fiber optic. So you can probably have a lower cost for copper wire, for instance, at a in exchange for the higher loss. So that's the balance that we have to find.
Okay, thank you. Any question from participants? You can ask directly Dr. Hafiz, don't ask me. Okay, tak ada soalan.
Okay.
Tak ada
Tak ada.
Okay. Okay, thank you. Ladies and gentlemen, we have come to the end of today's seminar. I would like to thank the speaker for the wonderful share and to all the participants for sparing your time to join our session today. I hope that everybody had a good time and we look forward to your participation in your future seminars. We will close our session with Tasbih Kafara and Surah Al-As.